Good day, everyone. Welcome to ME160 Undamped Harmonic Excitation. So, I hope you're having a blast today because we don't have in person classes for now. So, I've stated the reason why we're not meeting right now. But nevertheless, I hope you managed to pick up something from this asynchronous lecture. So, before we talk about undamped harmonic excitation, let's go into a bit of prerequisite. What do I mean by harmonic excitation? So, in ME160 at least, I use harmonic excitation and forced response interchangeably, which would not be the case, but the forced response refers to the response of the system to harmonic excitation. So, when we hear of harmonic excitation, it's going to be the disturbance. So, harmonic refers to simple harmonic motion. So, you have a sinusoidal disturbance, which evolves over time. And of course, the excitation part. It's a disturbance. Now, this is the disturbance required to produce forced response. So they vary with respect to force input, and they tend to not just add energy at the start but add energy throughout the active run of the disturbance. So the disturbance can be summed up or modeled as a simple sinusoid function f of t. So this is the forcing function, and f of t is equal to f naught, or the forcing amplitude, times cosine omega t. Now, this omega is called the forcing. Oh, sorry. This omega is called the forcing frequency. And at this point, let's just distinguish all the frequencies that we've discussed so far. So the tip here is you have to be careful about the subscripts. So the first omega that we encountered, omega n, is the natural frequency. This is the natural beat of the system. And if you have damping, you have a little bit of distortion. So that is damped frequency. What's common between these two is that this is coming from the system. While omega, without any subscript at all, is coming from the disturbance. So that, just to point that out, omega is from the disturbance, not from the system. All right. So where can I, as an engineer, observe harmonic excitation? So around our industry, there are actually plenty of sources of harmonic excitation. One of them could be a badly balanced fan, badly balanced impeller. So this results in a lot of shaking, and it will be high frequency shaking, knowing the speeds at which fans and impellers actually run. So depending on the integrity of your component, it could fall apart and fall apart catastrophically if nothing is done. But if it's just sturdy enough, but it still produces a vibration, that will be detrimental in the long run for your entire system. So this rotating unbalance, it can be due to manufacturing defects, or it can be an unavoidable part of the system. So like for example, you have a reciprocating piston engine. There is an unbalance per cycle caused by the up and down motion of the piston. So it's part of the process, it's part of the function. You don't want to get rid of it because that is why you employ it. So rather than eliminating the piston, you just do everything that you can to mitigate the vibration from the pistons themselves. Another example here is a stone crusher. So the stone crusher crushes stone, and this mechanism that is shown here is driven by a force imbalance. So just like with the piston engine, it is part of the feature, the vibration. So you just have to mitigate it from doing anything else that you don't intend. Another source of harmonic excitation would be flows of fluid, whether it's external or internal flow. So yes, piping systems can get very giddy. Another source of harmonic excitation is the ground or your factory floor. Vibrations can travel to the floor, and it can disrupt mounted systems. It can disrupt buildings, structures, hence why we build protections for our high-rise structures. And another surprising source of harmonic excitation would be the machining chatter. Whenever you drill, whenever you mill, actually, the tools and the workpiece might experience some level of vibration. And this can be detrimental in the long run if your tool bits tend to vibrate too much or your workpiece vibrates too much. You can get defective pieces, or you can get tool bits that wear out too quickly. So these are just some illustrations of harmonic excitation sources. There are probably more. Maybe these are just subcategories beneath these examples shown, but there could be even more, actually. Could be more examples. Now, all right. Oh, sorry. All right. Let's go to the equation. So, how do we model harmonic excitation? So, before we get into the general form, which we won't tackle for ME160 right now, we will content ourselves with a vibration or a disturbance that only has a single frequency. So, again, we will just assume that our disturbance is of a single frequency. So here in this case, we have a linear system. So again, for now, we'll take off damping to make things easier. So here you have a mass and you have a spring that is restraining the mass. And now what's new here is that you have a disturbing forcing function f of t that is making the system move. Now, if you convert it into a free body diagram type of equation, you end up with this form. And if you move around variables, you will get this equation of motion. So now it looks like a non-homogeneous linear differential equation. So now, because you have a non-homogeneous differential equation, you will have two components of your response. The first is the complementary solution, which comes from the system itself. It is the system vibrating to its own tune. And the second one, the more interesting one, is the particular solution. Right now, we will call it the steady state response or the steady state solution. Right now, since we don't have damping, it appears that the free response solution is also a steady state. It doesn't die down over time. But if we introduce damping, eventually this free response part of your response will eventually die out, and it will leave the steady state response as the sole behavior of your system. So that's a bit of a spoiler, but there we go. Now, let's look at the equation of motion and let's see if we can derive the response of your system. So, by doing so, you'll have to go through the non-homogeneous linear differential equation methods. So, one of the methods that we can employ is MUC. So, we define our unknown x p of t as x cosine omega t for now, x cosine omega t, and we also get its second order derivative, negative omega squared times the same function xp of t. We're going to substitute this into the equation and then solve for the value of x. So by doing so, we get this definition. So this is the amplitude of the steady state part of your response. So what you see here is that you have the forcing amplitude as the numerator and the system properties plus the forcing frequency from the disturbance in the denominator. So we can go ahead and simplify this further if we divide all sides of the fraction by mass. We will get this form. X here is the steady state amplitude again, and little f naught here is your specific forcing amplitude. So this is newtons per kilogram. Below, you have a difference of squares of different frequencies. It's a difference between the square of the natural frequency and the square of the forcing frequency. It's all right. Next, let's get the total response now. So here is the total response. There's a free part and there's a steady state part. Now, in order to get A1 and A2, in this case, we of course go to initial conditions. Assuming they're not zero, we can derive them. By substituting this back into the general equation, we finally get the proper definition. So this is the total response of your system. You have three terms if all initial conditions are non-zero. So what you notice here is that uh, even though you have a distinction between the free response part and the steady state part, your free response is being affected by properties from the steady state response. So, NSI 21 wise, you can think of this as the non homogeneous coefficients being not the same as the homogeneous coefficients. It's kind of like that. So, the steady state response actually, no, rather, the harmonic excitation actually changes the way the system behaves in its free response portion. All right. So let's jump into an example. So this example is in your module. It is example 5-1. It's in page 3 of your module. So I'm going to read out the example from here. So right, we have a mass spring element. No, rather, it's a mass spring system of mass 5 kilograms and a spring rate of 20 kilonewton per meter, and it is excited by a completely reversing force of 50 newtons, completing a sinusoidal cycle every zero point 0.1 seconds. Now, the initial conditions are as follows. Your initial displacement is equal to 1 meter, and your initial velocity is negative 2 meters per second. Find the total response of your system. So, okay, I'm gonna give you some time if you want to solve it yourself. If you want to follow along the module, you can pause now and then come back here to check your solution or, have a break. So here, it is important that, especially for a an equation heavy course such as ME 160, is that when we're given a problem, the first thing that we need to do is to pull out the equations, the formulas that might be necessary for the solving of said problem. So the first thing that we're going to pull out is the general form of the forced response. So you have here two terms of the free response portion and the third term, the steady state response portion. Next, we identify the unknowns. What part of this equation do we not know yet? So we know the initial conditions. So x naught and x dot naught are given. We don't know the specific amplitude, f naught. We don't know the natural frequency yet. And we don't know the forcing amplitude. However, if you notice here, these three unknowns, they actually come in very easy. How do I solve for the specific amplitude? The specific forcing amplitude, I mean. The specific forcing amplitude is just the forcing amplitude divided by the mass. So we have your forcing amplitude, it's 50 newtons. We just divided by 5 kilograms. The natural frequency, I hope you take this into heart. The natural frequency is just the square root of the fraction of the stiffness over the mass, at least for linear systems. So we have a stiffness, we have a mass, ratio them, and take the square root. For the forcing amplitude, this one is a little tricky, but we are given a time-related property of our forcing response. So it says here in the problem that our forcing amplitude, our disturbance completes a cycle every zero point 0.1 seconds. So that is the period, the forcing period of your disturbance. So how do we get the forcing amplitude, or sorry, not forcing amplitude, the forcing frequency from this? we just take 2 pi and then divide it by the period to get the forcing frequency that is in rads per second. So, all right. This is actually easy. So the next thing that you have to do is just fill in the unknowns and make sure that there are no variables that stay inside this function aside from time t. So what you'd end up with is this. This is now your total response to the disturbance. All right, so what does this response look like? So here will be the defining difference between forced response and the free response. This is what your system response would look like. Yeah, it looks like a very tight wave. So here's the thing. With free response, it's really easy to interpret the graph at the time domain. But now since we have a forcing disturbance that evolves over time, sometimes it can be a doozy to interpret what your response is in the time domain. Now we won't tackle that part just yet, but there is a way to interpret the response of a system under harmonic excitation without having to go through the time domain. For now, let's just enjoy how it looks like. So it kind of looks like a sideways hourglass, I guess. Sideways hourglass. All right. So let's go to the next example. Okay, so we have example 5 2. It's just the next page from the previous example. So here we're given a mass spring system. We don't know the mass, but we do know the stiffness. It's 45 kilonewton per meter. So since we don't know the mass, we're going to figure it out by vibrating the entire system from rest. So we're going to vibrate it with an amplitude of 30 newtons and 20 hertz. Now, the developed amplitude of your system is zero point 0.2 meters. Find the mass of your system. Okay, it's good that the slides actually note what the initial conditions are. It might not be obvious for you, but if something starts from rest, that means all of your initial conditions are zero essentially. So what do we do with this one? Of course, since this is an equation heavy course, we pull out the expressions, the formulas that we might need for the solving of this problem. So yes, we also have the response. The total amplitude is zero point 0.2 meters. All right, so this is the general response. Alright, so what do we do with this? How do you solve for the mass? Now the mass can be anywhere at this point. So if you notice, where could the mass be hiding in this equation? It could be hiding in the little f naught here, the specific forcing amplitude. It can also hide in the natural frequency, omega n. How do we narrow this down? There is a way, but first let's try to simplify our response. We know that the initial conditions are actually nil, so we can remove some terms here. So the second term is totally gone. This is all that we have. And if you notice, we have similar fractions, so we can just group the two cosine terms together. Here we go. All right. So does this solve our problem? Not quite. So it says here that our developed amplitude for the total amplitude is zero point 0.2 meters. Now the question would be, whose amplitude is it? Is it the amplitude of the free response or the steady state response? So when you have no damping at all, uh, there is no clear answer. It might as well be both of them. So you can't just take this coefficient fraction here and say, oh, this is zero point 0.2 meters then. You still have a difference of sinusoidal terms. To be prudent, we have to express this difference of cosines as a single term. So how do we do that? I recently confirmed that not all senior high schools go through this set of equations, but in case you're curious, there is this trigonometric identity called product to sum to product. So here it is. These are the forms. So we can use this to transform our difference of cosines into a single term, albeit it's just a sinusoidal term times another sinusoidal term. So we have a cosine minus cosine situation. So we're going to use the third row in this formula. So we have this. All right. So is the coefficient now the total amplitude? Yes, you can now take it as the total amplitude. The next step would be probably multiplying everything by mass. When you multiply everything by mass, uh, or rather multiply both sides of the fraction by mass, you revert to the original form of the steady state amplitude. It's just going to be 2 times big F naught over, I think this would be K. Yeah, I think this would be K minus M omega squared. So instead of having two terms that can potentially hide your mass, you now only have one term that carries the unknown mass M. So that value of mass, wait, let me see if it's actually here. Oh, right. So here we go. We're going to simplify it. Just in case you're confused, let me see what's happening. All right. So instead of omega squared, we opened it up to become 2 pi f. So if you recall, the angular frequency omega is equal to 2 pi cyclical or rotational frequency, 2 pi f. So by doing so, we can further simplify. We can use the frequency 20 hertz immediately instead of having to convert it separately. So as we continue on, mass is now just in one term, and we just have to rearrange the expression to get an expression for mass. And here it is. So if you do your equation manipulation right, you just plug this in, plug in all the known values, and you will get the value of 2.83 kilograms. What does the response looks like? This is like one big eye. You can see that you start from rest. Like it's kind of obvious, and it's just a big squirgle of waves, and that's pretty much it. All right. So now, we're going to talk about frequency, the forcing frequency versus the amplitude that it generates. But before then, I hope you take a break for now, and you can peruse the videos that I will attach to this asynchronous lecture. Please do so, as it gives you some of the context that you might need, real examples that are on video that you can at least use to interpret what we are examining in this lecture. All right, so here we go. This formula again is the steady state amplitude. So this is x. It is equal to the fraction of the specific forcing function over the difference of squares between the natural frequency and the forcing frequency. Now you've seen the time domain response. It's kind of squiggly. It's hard to interpret, but there is a way. Instead of interpreting everything with respect to time, we're going to interpret amplitude with respect to frequency. So the natural frequency again is a system property. Your forcing frequency is something that's contributed by the disturbance. What's the difference? The system property can't easily be changed, but the forcing frequency is potentially you can adjust it. So this is the more adjustable of the frequencies. So what we're going to do, uh, we're going to model what we call a sine sweep or a frequency sweep. We're going to see the behavior of the steady state amplitude x as the forcing frequency changes. So again, we're going to model the change in steady state amplitude x with respect to forcing frequency omega. Um, Although you might expect, oh, how is this going to help? It will help much more than just staring at the time domain response. So before we do so, let's generalize our variables. Rather, not generalize. We're going to normalize our select properties. So instead of using steady state amplitude outright, we're going to normalize it to make it dimensionless. Same with the frequency. So in order to do that, we're going to define this ratio called the frequency ratio R. So take note, this is another R, but from this point on, R will be mostly the frequency ratio. For the overdamped response, I just picked R at random because some reference chose it. Okay, so I didn't pick it at random. So I think the reference picked it at random. Maybe they didn't anticipate using R for the frequency ratio. All right. So if we do this, in order to make R appear inside the steady state amplitude equation, we're going to have to do a few things. First, we're going to divide all sides of the fraction by omega n squared. This eliminates your omega n squared term. It becomes 1. And the second term, the minus omega squared, it becomes minus r squared. So now what happened here? So instead of just leaving omega n squared that's stuck with the specific forcing amplitude, we opened it up, we turned it into k over m, and we simplified the fraction. Now, in order to normalize steady state amplitude x, what you'd notice here is that uh, specific forcing amplitude is multiplied to the mass. And again, what is the specific forcing amplitude? It is the force over the mass. So that essentially turns it into big F naught again. So if you turn it into big F naught again, you'll get F naught over K, F naught over stiffness. And what does this look like? It kind of looks like a deflection equation. So if you recall Hooke's law, F equals the stiffness times the displacement. So it kind of looks like that. So what we're going to do is if we divide F naught over K, we get a displacement term. And we're going to use that to normalize our steady state amplitude X. So if we do so, we will get a brand new normalized term. So if the forcing frequency gets the frequency ratio, the steady state amplitude gets the magnification. So this is the definition of magnification in terms of the frequency ratio. So the difference between x and m is that m is the normalized version of x with its function being in terms of the frequency ratio r. So the neat thing about having things normalized is that you can compare systems with different properties from one another. And if you normalize them, you'll see that some of their behaviors tend to coincide with one another, regardless of what their mass is, regardless of what their stiffness is. You can express a general model for their behavior. So what happens is that we can graph this and it represents, or at least it accurately represents the behavior of the single degree of freedom system under harmonic excitation for all conditions. So if we graph this, we graph R as the x-axis, M as the y-axis, we get this particular graph. Whoa, what happened here? So if you notice here, you have this part here that starts at 1 and it just shoots up at a value of R equals 1. And then after 1, it kind of goes back from negative infinity. And then as you increase the frequency ratio, it just peters to 0. So what's happening here? First and foremost, if we go back to the equation of m, you have a difference underneath the fraction. So if that difference becomes 0, you'll get an infinite value, or rather, you'll get an indeterminate amount of value. And the value of R that causes your magnification to go wild is actually the natural frequency. So if your forcing frequency happens to find the natural frequency, your entire system will go wild. And because it is such a distinct part of the behavior of systems under harmonic excitation, we can actually define the rest of the regime, the behavior regime, in accordance to the value of omega with respect to omega n. Or in this case, with respect to the value of r equals 1. All right, let's look at the excitation cases. So we're going to examine each part of the graph, or rather each zone of the graph. So here is our first case. What if your forcing frequency is much less than the natural frequency? In essence, you're in the left zone. You're in the left zone here. So if you're in the left zone, some things kind of happen with the response. So first and foremost, since your forcing frequency is a lot smaller than the natural frequency, it tends to be the big brother sine wave to your free response. So if you see here, black here is the total response. Your free response portion is actually quite tight. It's kind of quite small. But your steady state response, the one swaying to for the forcing frequency omega, it's kind of big. So for case 1, steady state wave acts as a spine for the free response to conform to. And the thing about the forcing function and the steady state function is that they are in phase. So this is steady state part of your response, and this is the disturbance itself, and they are in phase. That is interesting. And if you notice here, in our graph, the smallest possible value of your magnification is 1. And any other movement will just increase your magnification further. What is the implication of this to our system? So what happens is that if it just so happens that your machine is being disturbed by a frequency lower than its natural, technically it's kind of safe, but not so much. If you see here, the magnification is greater than or equal to 1. It's okay, but it's not good enough. You don't want your system to operate here in this zone. Like it's possible to stay here, but it's not ideal. It's not ideal for the system. This is the opposite case for the other side when your natural frequency is now much smaller than your forcing frequency. What happens here is that the free response and the steady state response, they switch places. Now the natural frequency is the spine of your total response, while the steady state is kind of like the little brother that follows the big brother's lead. So yeah, this is the case. And if we observe the phasing of the steady state response with the disturbance, you can see that it's flipped. The phase of the disturbance is 180 degrees out of phase with the steady state response. So also, if you notice here, even though you come from infinite after you leave the value the frequency ratio 1, any further increase in the forcing frequency and your magnification is just getting smaller and smaller and smaller. So if you compare the steady state value of the response for case 2 versus case 1, let's look at case 1's. This one is zero point 0.3. For this one, it's zero point zero 0.02. So in this zone, if your forcing frequency is greater than your natural frequency, you encounter some vibration, but it's not really that bad. Hence, this is where you'd want to operate your system. You want to have if you can't avoid disturbances, you can't avoid frequencies. You want to make sure that the frequency that is the source of disturbance is greater than the natural frequency or natural frequencies of your system. So case 2 is the default zone. This is the safe spot for most machine designers and system or plant managers. So right, so that's case 2. So we've explored what's at the left of r equals 1. We've explored what's right of r equals 1. Let's look at r equals 1 itself. So for this, uh, we're we're going to run into some problems with the function. So we're going to have to deploy something that you may not have used for a while. This is L'Hopital's rule essentially. So uh, if we do L'Hopital's rule and then assume that the system starts from rest, we end up with this equation. This is the general response, the total response, I mean, of your system under harmonic excitation. And we can simplify this further using L'Hopital's rule. But before then, we kind of group around certain variables. All right, after we do that, we do some further simplifications and then we apply L'Hopital's rule. So if you have a fraction that is kind of weird, if you take the value of this fraction at a specific value and it explodes into infinity, what you can do is take the limit of the first order derivatives of the numerator and the denominator separately. So our unknown value here or our variable to differentiate would be the forcing frequency, not t, the forcing frequency. So if you do that, we end up with this fraction. How did we get here? You can for sure review your calculus. I don't know if this is in senior high or in the first math or the second math. I'm not sure. Now, if we do this, we will get a function that doesn't blow up immediately. And we can use this to define the response of our system when your forcing frequency is right at the natural frequency. You will get this form. Now, what is the problem with this form? So, this is a function of time. So, you have a sign that is a function of time. That's nothing new. But you have um, the time response t multiplied directly to the sine function. So it's not decaying, it is actually just left as is. So what's going to happen here is that as you increase time t, this value of t will just grow and grow and grow, and your response would kind of look like this. It will blow up like this. So, right. Oh, where did this come from? This is actually the steady state. This part is the steady state. No, no, no. This is not the steady state response. This is the converted steady state response of your system. This is just for if your initial conditions are not zero. All right. So this is what happens. The vibration grows and grows, and then it collapses. What do we call this case? This is resonance. If you've heard resonance before, this is when it happens. When you strum a system according to its tune, when you strum it, essentially when you strummed it, you hit the natural frequency, and now it wants to sway violently. The thing to note here is that according to our model, systems under resonance will not collapse immediately, at least systems that can offer some sort of springiness. It won't collapse immediately. However, if you stay in the resonance zone, you're dead, essentially. Your system is dead. Why is this beneficial for us? For example, you're a plant operator and you're going to switch on a motor. You're going to switch on a motor. What is the frequency of a motor from essentially no power? It's going to be 0. So in this axis, you're going to start from 0. And in order to reach your operational frequency, let's say your operational frequency has a ratio of 3. So we're going to get from 0 to 3. You're going to pass through here up to the danger zone, then to 3. If your system immediately collapses when it hits 1, uh, all of us are doomed. Like, there will be no motor, no engine to start, essentially. Because we have a time delay from exposure to destruction, we can just quickly pass through this zone without much worry. So just make sure that you don't stay in resonance, else something bad will happen. So this is what could happen. You could get swaying, especially for Tacoma Narrows here. It encountered an aeroelastic flutter that uh, caused a harmonic disturbance that is the same natural frequency as the bridge. So it swayed and then it collapsed. Another resonance phenomenon is ground resonance. It occurs when a helicopter kind of hits the right tempo. When I say hit the right tempo, it's landing gear hits the ground at a particular timing, and it causes the pressure waves from that contact to reverberate with the natural frequency of the helicopter. So it's just gonna go kaput, essentially. So if you see here, the resonance kind of takes its time. It's not going to be instant, but it will destroy your system because the vibration gets worse and worse. So that's resonance for you. Now, you might have noticed something about how I shaded the first two regions. It's in a gradient, sort of. So there's something unique that happens when you approach resonance. So, in order to examine this phenomenon, we're going to start from rest. All of our ICs will be 0. So if we do that, we just get this form, which we got from example 5.2. And what's going to happen here is that we are going to have a specific assumption. Because your forcing frequency is nearing the natural frequency, we can make the following simplifications. So first and foremost, if we add up the forcing frequency and the natural frequency, we can kind of assume that it's just twice the forcing, right? And then the second assumption, we can assume that if we subtract the forcing frequency by the natural frequency and then take half of that difference, we get some new term called epsilon. I will just label it as epsilon for now. And oh, okay, so I unleashed the name of this epsilon. It's called the beat frequency. All right. So we'll call epsilon the beat frequency. So if we substitute this to our existing equation here, whoop, we can get this relation as well also. So omega n squared minus omega squared is equal to essentially sum of this identity of difference of squares. So we can put in our relationships, substitute them, we get this new expression for omega n squared minus omega squared. Now, putting it all in, we get this new form. Oh, what's happened? So let's see what happens. So this kind of sinusoid, this kind of sinusoid function is a sine multiplied to a sine. What's happening here is that there is a little sine wave that is being clamped down by a bigger sine wave. So this is not like case 1 or case 2 where the bigger sine leads to smaller sine. This case, the smaller sine gets clamped by the bigger sine value. So what does it look like? It looks like this. So you have a big sine. This big sine is following the beat frequency. This again, your epsilon. And your total response is yeah, essentially being squeezed by this invisible beat frequency. Why do I call it invisible? Because if you look at your original equation, there's nothing, no, there's no part of your system that's actually directly producing the beat frequency, but it just appeared in the response. Essentially, if you can play two frequencies at 1 hertz or more apart, you your brain kind of enters this phase where it kind of hallucinates a frequency that isn't there. This is the concept behind binaural beats essentially. So you play one frequency in your left ear, one frequency in your right, and the difference it causes an illusory frequency, a low frequency, and that is where the binaural beat comes from. Will Is it that relevant to systems? Not so much. Case one, case two, case three matters more, but it's kind of an interesting thing to see. And is that it? Yes, that's it. That's it for this lecture. I think we might recap this a little bit before we start off with the next part of harmonic excitation. But until then, thank you so much. Have a great day.